And we have 2 exciting weeks ahead of us with interesting lectures by spectacular speakers, and I'm sure we'll learn a lot. So the purpose of this talk is basically to give kind of either an introduction or a summary to try to put everything in perspective, kind of a brief, broad brush picture of where we are in particle physics. So it will be a summary of where we are, a little bit of a historical perspective. I think I'm almost the oldest person in this room now. And so I can give some historical perspective, and the time scale I'll have is the last 35 years, where I'll describe what happened 35 years ago, and I'll contrast that with the situation today. So this will be how we got here. I will also summarize the problems and the challenges the standard model of particle physics poses, where we are, where we were as far as these problems are concerned 35 years ago, and compare that with the situation today. I'll give you a glimpse of what I will say. We haven't made much progress on that account in the last 35 years. And then where we might be heading, and we'll see that, again, the summary will be that we are at a junction that very soon, within a few years, and Nima already alluded to the next round of the LHC, we'll have a clear indication of a very deep physics/philosophical question about nature. And that would be the main topic of the talk. So what you will not hear in this talk, there will be no new experimental information. I leave that to my colleagues who will talk later in this school. No new theoretical computations or new models or new concepts. Unfortunately, I have nothing to offer. So I will only talk about things that are well known and trying to wrap things up in a way that will be easy to remember, because you will hear during these 2 weeks many speakers with many points of view talking about different extensions of the standard model and different experimental techniques. And sometimes it's hard to keep all these things in mind. So as always with such summaries, I try to organize things into boxes, into different categories, and that's never completely precise because there are things that are in between categories. And if I try to make blanket statements, there are always a lot of caveats. The statements are not always true. I'll mention some of them. So the first question we would like to address is regarding the discovery of the Higgs. I'm sure all of you heard about that. So the first question, is it the Higgs? Well, now it's official. As of March 14th, CERN announced that the new particle is looking more and more like a Higgs boson. So this is clearly a Higgs particle. It looks a lot like the Higgs. It walks like a Higgs, talks like a Higgs. So it is a Higgs. The next question is not, is it a Higgs, but a more detailed question, is it the Higgs? So there's a big important difference here in the D. Is this the Higgs of the standard model? So it seems that the standard model, the minimal standard model with a single Higgs, the simplest thing we can write down, seems to work extremely well. And as far as I know, we don't have really any overwhelming evidence that it's wrong. So for the rest of this talk, we'll take the working assumption that the standard model is at least a very accurate, or at least approximate description of nature. And all we are after now are the small deviations from this approximate description. So what are the options for the near future? What can the LHC find? And in that I mean the further analysis of the existing data, which will gradually come during the coming years, and the next run. So option number 1 is nothing beyond the standard model in its single Higgs. They will run the experiment, and everything will just work better and better. The error bars will get smaller, no new particle, no new data. Second option, we'll find something that goes beyond the standard model. And that can come from various different directions. First, there can be discrepancies in the Higgs couplings. People measure the Higgs production rate and the Higgs decay rates in various channels. And there could be a discrepancy there between the measured value and the theory. There can also be discrepancies in other processes. More dramatic things that can happen, we'll find additional particles, new resonances. Any particle beyond the minimal standard model will be great news, and we'll have to really try and think what it means. There could also be progress in dark matter physics, progress in dark matter, experimental progress, discovery of some WIMPs, for example. Such WIMPs might or might not be related to electroweak breaking. I will not discuss it here. Now, many of the other speakers in this conference, in this school, sorry, will address many of these questions. We'll see how the Higgs production rate and decay rate and the branching ratios are measured, what we can learn from that, what other more precise measurements of processes and where we can look for discrepancies, how this is done, how we look for additional particles, and there will be even a series of lectures about dark matter. So since I'm giving an overview here, I'm not going to spend too much time discussing that. When we talk about extending the standard model, again, we would like to organize it into boxes, so how to think about that, and we'd like to various categories. So the first thing to do is to organize it in terms of the spins of the new particles. So the first possibility is finding additional scalars, and the typical example that people contemplate is the existence of a 2 Higgs doublet model. In the minimal standard model, we have only 1 doublet. We can contemplate having 2 doublets, and every once in a while we hear rumors that another Higgs was found. Maybe it's true, maybe it's not. Maybe we'll hear more about it in this school. So this is this possibility of additional scalars. Another possibility is additional fermions. There could be massive vector-like particles. For example, another doublet. It's not in a chiral representation of the standard model gauge group, therefore there's no problem giving it a mass, and it could be just fermions sitting there. We don't know why it's there, we don't expect it to be there, but for all we know, it could be there. And historically, particle physics was faced with new particles that had no reason to be there, but happened to be there. And people ask, who ordered that? So something like that could happen. So this is spin 0 and spin 1/2. People explored such possibilities. Going up in spins, there could be spin 1. The typical example here is denoted is called a Z prime, another U1 gauge field with various couplings to the standard model. People look for Z prime, the bounds keep improving, but the LHC could still discover it. Could even be higher spin. There's a lot of interest in the existence of spin 3/2 particle. Maybe we'll hear about it later here. There could also be spin 2, Kaluza-Klein gravitons, and all sorts of fancier theories. So that's what we look for, but what we're really interested in is not just finding another particle, but a particle that points to a new conceptual extension of the standard model. We can have new symmetries, like new gauge forces, and I'll mention some of these possibilities later in the talk. We can also have extensions of the symmetries of space and time, like supersymmetry or extra dimensions. And there could be something else that we haven't yet thought about, and we should not underestimate nature's ability to surprise us with things that we, poor theorists, couldn't figure out or couldn't anticipate. So what are the more conceptual extensions that people considered? Option number 1, so again, I had to divide it into categories, and if I divided the particles by spin, I divide the categories of extensions of the standard model depending on whether the coupling constant is large or small. Sorry. So option number 1 is supersymmetry. We'll hear a lot more about it later in this school. And the hallmark here is that supersymmetry is weakly coupled. Option number 2 is strong coupling. And that comes under various different names. Historically, it started with the name Technicolor. This was the idea that there's some strong coupling dynamics at the TeV range responsible for electroweak symmetry breaking. The more modern incarnation of Technicolor, it comes under the name of warped extra dimensions. This is exactly the same as Technicolor. It's some strongly coupled theory in the TeV range that has the property that it has a gravitational dual that makes it easy to analyze its strong coupling. So this is another option. So either we have supersymmetry, which is weakly coupled, or some strong dynamics. And I think this is where I will put the money, on something else we haven't yet thought about. And you will see later why I think this is an interesting and viable possibility. So again, supersymmetry and Technicolor, or weak coupling and strong coupling, or something else we haven't yet thought about. So I'd like to give a one-line summary, because in such 2 weeks, it's hard to remember everything you will learn. And even in one talk, it's hard to get a summary. So I always like in talks to give one slogan, one line that really captures the main point, or at least one of the main points. And the problem with such one-line summaries is that they are never completely accurate. They are always if, ands, and buts. So if we ignore the if, ands, and buts, and we just want to get a broad part picture, this is my summary. The measurement of the Higgs mass, 125 GeV, is uncomfortably high for supersymmetry and uncomfortably low for strong dynamics. Strong dynamics wants the Higgs to be heavy. Supersymmetry wants the Higgs to be light, and 125 is somewhere in between, uncomfortable for both. And I use the word uncomfortable. I did not say just too heavy or too light, because there are still various ways around it. But as a broad brush picture, this is the summary. And now I'm going to give a lot more details, so more details below, but let us start from the beginning. Where are we in particle physics? What are the issues, and how we got to where we are, and how we expect to continue? So the standard model of particle physics is extremely successful. Many experimental, literally trillions and trillions of experimental results confirming it. No known discrepancy between theory and experiment, and unprecedented accuracy. Some objects are calculated and measured to many, many significant digits, showing that we really know what we are doing. The various dipole moments are examples, but there are many others. What are the problems in the standard model? So the first question is, where did the spectrum of particles come from? And here I divided it into 3 categories. First, the gauge group. We have the gauge group SU3 cross SU2 cross U1. Where did this come from? Why do we have this gauge symmetry? Why do we have gauge principles in the first place? But if so, why this group? And if you wanted to have a group, that would not be your first guess. There are many other groups which are simpler, nicer, bigger. And so that's the first question. The quarks and leptons also have bizarre quantum numbers, 3, 2, 3 bar, 1, etc. Where did this spectrum of particles come from? And why does this whole structure repeat itself 3 times? So these are kind of more qualitative or discrete choices. We had to pick a gauge group. We had to pick particle representations. Why did nature pick this choice and not something else? That's an interesting question, and I think it is fair to say we don't know. Second question is of a somewhat different flavor, and that's what determines the electroweak scale. So here we have 3 particles, the Higgs, the W and the Z bosons. What sets the scale of electroweak symmetry breaking? Why is the symmetry broken? Why do we have these particles? What sets their mass? And I'll have a lot more to say about that later, although I'm not going to give an answer. Then there is a more detailed question about Yukawa couplings. Most of the parameters in the standard model are in the Yukawa couplings. They couple these particles, the Higgs, to the various quarks and leptons. And there are a lot of parameters here, and they lead to fermion masses. They lead to mixing angles. They lead to CP violation and to many other things. And again, we have all these numbers that nature tells us what they are. We know their values, and we don't know where these numbers come from. Next class of questions will really occupy most of the rest of the talk, and that's a question of hierarchies here. The standard model parameters exhibit a whole variety of hierarchies of different kinds, and I'll show that there is a hierarchy of hierarchies here. First, hierarchy in quark and lepton masses. The lightest lepton is the electron, if we ignore neutrinos for this purpose. We ignore neutrinos, then the mass of the electron is what it is. The heaviest of them is the top quark, and the ratio between them is about 5 orders of magnitude. So that's very surprising. The numbers of masses, the values of these masses span 5 orders of magnitude with no understanding at the moment where these numbers come from. It's not that one of them is 3 and the other is 5 and another one is maybe 7 and the third one is 0.5, but they span 5 orders of magnitude and we don't know why. Related to that is this pattern of CKM metrics, the mixing angles between the quarks. These are small numbers, not as small as 5 orders of magnitude, but these are small numbers. Again, there is a pattern there. Nearby generations mix slightly. Faraway generations, kind of separated by 2 units, are mixed less strongly, and we don't know why it is so. This is a problem of a slightly different nature. It's theta QCD. We can add a parameter to the standard model responsible for CP violation in the strong sector. Strong interactions can violate CP. And the measured value of this number is, the latest is less than 10 to the minus 11, and the number keeps getting smaller and smaller. For all we know, it could be exactly 0, and we don't know why the number is so small. Where did this 10 to the minus 11 come from? And if this is an angle, so it could be any number between 0 and 2 pi, it could be in 0.3 or 2. Okay, that's the value of the parameter. But 10 to the minus 11 really begs for an explanation. Where did this small number come from? And the last hierarchy here, so all these are small numbers, we don't know why they are there and why they are so small, is the electroweak scale and the Higgs mass, and I'll say more about all these hierarchies later. The next question, so remember the spectrum was the discrete choice of the spectrum of particles, then there were continuous parameters that we don't understand, and these parameters exhibit a hierarchy, kind of big discrepancy of scales, and we don't understand why. There's a whole collection of questions associated with dark matter. You will hear about it more from the speakers. And this is a point that is really beyond the standard model. I'll say very little about it. It's neutrino masses and mixing angles. The main thing here is that A, it goes beyond the standard model, really proving that the standard model is incomplete. Even if we leave out gravity, this is a solid experimental evidence that the standard model is incomplete, pointing to higher scale in which new physics takes place. And the other thing which is interesting here is that if we look at the mixing angles here, they are not small. Here they are really numbers of order 1, which is unlike what we see in the quark sector. So I'm just looking at the numbers. I have no interpretation, but if I had a prejudice that mixing angles are always small, well, they're not. And if they're not small here, they're order 1 here. Why aren't they order 1 here? So being so old, I'd like to give a historical perspective. And that's more or less when I learned about the standard model. That's why I put this very selfish, egocentric way, put the boundary of 35 years ago. So 35 years ago, all these problems were known. So that was in the late 70s. Almost every one of them, there's slight discrepancy. The issue of neutrino masses, it was not completely established. It was not experimentally established, and even theoretically it was not completely understood that they are not zero. But with the exception of that, every single one of the other questions were known. So that doesn't look good, 35 years, and still don't know the answer. And despite a lot of progress, it's fair to say that we still don't have a clue about these questions. So we asked ourselves these questions 35 years ago, and we still face exactly the same questions. You should view that as a challenge and an opportunity. You are younger, you can do better than the previous generation. Our best chance, I think, to make progress here is to get clues from experiment, and the experiment is coming. So we don't know which of these questions will have an answer coming from experiment, but whatever it is will be welcome. The LHC has been working extremely well. The machine and the detectors work extremely well, and there's every reason to expect that it will work very well in the second run, and we'll know what it is that lies out there in the TeV range, and we hope it will give us something, some clue to answering these questions. But actually, we should be a little bit more careful. It's not true that we have made no progress during the past 35 years. So I'm going to devote the next 2 slides to the experimental and kind of a summary of a theoretical and experimental progress in the last 35 years from my very biased personal perspective. So we'll start with the experimental progress. And here I think it's really spectacular. Compared with 35 years ago, all the parameters in the standard model are known. 35 years ago, we did not know the mass of the top. We did not know the mass of the W and the Z. We expected them to be in some place, but they were not measured. The mass of the Higgs was measured only recently. So this is the mass of the W's and D's. This was in the early 80s. The masses of all the quarks, finally the top was measured in the 90s. All quark mixing angles are known. People knew about the CKM metric, but we didn't know what the numbers were. And most recently, the Higgs mass. So this really nails down all the parameters in the standard model. We know what they are. There's no question that maybe the top is at 30 GeV, maybe it's at 100 GeV. We know what the values are. We can still make the error bar smaller, but we know what the numbers are. The second progress is neutrino masses and mixing angles. Again, 35 years ago, some people speculated that there could be neutrino masses. Now we know the masses. The masses were measured by several different processes, experiments of different flavor. We know the masses, we know the mixing angle. There's still a lot more work to be done here, but this is progress. A lot more information about dark matter. I think we have no doubt that dark matter exists. We don't know what it is. We don't know if it's a WIMP, and if it's a WIMP, we don't know what its mass is. But again, 35 years ago, the situation was a lot murkier than that. And the most surprising, again, from my perspective, is dark energy. This is, again, something that nobody expected 35 years ago. Now we know it's there. And I will say more about it later. And many other facts about cosmology. 35 years ago, cosmology was kind of almost backwater. Kind of It wasn't clear what it is. Even orders of magnitude didn't work. And today it's a precision science. People discuss the second decimal point, the third decimal point, etc. So that's the progress in experiment. If you look at that, I think we can really be proud of the achievements of the last 35 years. What about theory? I think we should be equally proud about that. And unfortunately, this is not directly related to the experiment, and it's not directly related to any of the problems / challenges I posed earlier. But we have made a lot of progress in the last 35 years, we as a community. First of all, we have much better understanding of quantum field theory, what's its dynamics, what its possible phases, how to calculate. Second, much better understanding of quantum gravity through string theory and its surprising properties. We'll learn a lot about how to compute in perturbation theory and string theory. We'll learn about string duality. We'll learn about ADS-CFT and all its consequences. And perhaps what's most surprising is the interconnections here, the connections between quantum field theory and string theory, connection between this and that, and connections between ideas in field theory and quantum gravity and ideas in modern mathematics. And historically, whenever there was a development that had applications in other branches of science, it was always an indication that there's something very deep going on that we are exploring, and we have this feeling here. So it's not true that we haven't done anything in the last 35 years. I think we can be extremely proud of these achievements. But this progress does not address the questions that I raised earlier. The next topic I'd like to discuss is the question of the hierarchy. I mentioned it earlier, the different hierarchies that we have. And the next n slides, and pretty large, I'll discuss the hierarchy problem from several different perspectives. And again, I'll take the historical route, starting the evolution through the 20th century of these ideas, and try and say where we are today in this. So in its simplest form, the hierarchy problem is the failure of dimensional analysis. So I have a pointer here, and I always like to do this experiment because it always works. I throw it up, and I catch it, and I ask, how high does it get? Well, on dimensional grounds, the answer should depend on the time it went up and on the acceleration of gravity. And just on dimensional grounds, the only combination of dimension of length we can form is gt squared, the acceleration times the time square. And then there's a number of order 1, which in this case turns out to be a half. In order to get the a half in front of it, one has to work a little bit harder than just to do the dimensional analysis. Well, to get the a half here is not a lot of work. In other cases, to get the number of order 1 is more challenging. Sometimes we need computer calculation, and sometimes we don't even have that. But dimensional analysis works in physics. The area of the circle, the circumference of the circle is 2 pi r. The r is there on dimensional grounds. The 2 pi is a number of order 1. And the same is true for other processes. It's very strange to have a situation where dimensional analysis is off by 10, 20, 30, or 100 orders of magnitude. We don't have a precedent of that in physics. Sometimes we have 1%. We are very surprised. We have to understand it. If the number, the dimensionless number, is extremely small or extremely large, it really begs for an explanation. So this is the simplest form of the understanding. And I think in this context, it's fair to give reference to Professor Dirac, who at the beginning of the 20th century knew of the proton mass, knew that the fundamental scale of physics is the Planck scale. And Professor Dirac noticed that there are 19 orders of magnitude between them. And he asked himself, where did this big ratio come from? And this is known as Dirac's large number problem. Why is the proton mass so much smaller than the Planck scale? On dimensional grounds, the fundamental scale is the Planck scale. The proton should be as heavy as the Planck scale, but it's not. It's 19 orders of magnitude smaller, and we need to know the answer to this question. And as always in science, the challenge is always to ask the right questions. Answering them is sometimes easier. So that was a great question, and it took some decades to find the answer. And today we actually know the answer to Dirac's question. The reason the proton is so much lighter than the Planck scale is because of asymptotic freedom. And this formula is the only way physicists know how to get very small numbers. We get very small numbers by taking an exponential e to the minus, a number of order 1 divided by g squared. G is the coupling constant, and a is some number depending on pi's. And we can get very small numbers by making g small, but not very small. So G, a small number, but not very small, can produce a tiny number for MP over M Planck. And we really know the answer to the Dirac question. So that's very nice, but there is a modern version of the same question. And the modern version involves the ratio between MW or MZ or MH, all of them are about 100 GeV, and the Planck scale, which is 10 to the 19th GeV. So we don't have a problem of 19 orders of magnitude, only 17 orders of magnitude. And in fact, if you look at the formulas, the thing that appears in the formula is not the mass, but the mass square. So the question here is not a number which is 10 to the minus 17, but the number we don't understand is 10 to the minus 34, and we really need to find an explanation. And all the explanations that people contemplated really rely on the same formula. As I said, this is the only way physicists know how to produce very small numbers. We produce very small numbers by such an exponential function. And all the explanations, let it be technicolor or supersymmetry, always try to produce a formula like that with an exponent. So more generally, this is the intuitive hierarchy problem. Where did these small dimensionless couplings come from? How come nature gives us something in which dimensional analysis is so wrong? And we have to understand why. Continuing in a historical order, I think the next milestone in this development was a series of 2 papers by Weisskopf, where he computed the self-energy of the electron. And in the first paper, he actually got it wrong. He found a power divergence. In the second paper, he got it right, and he found a logarithmic divergence. And then he came to the understanding that power divergences in quantum field theory are bad, logarithmic divergences are good, and therefore this should be a principle that we should pursue. We don't like power divergences, and that was sometimes in the 30s. I don't think there was a deep understanding of the renormalization group and what do power divergences mean and so forth at the time, but that came a little later with the next milestone by Wilson, who unfortunately passed away recently. And Wilson really understood the renormalization group a lot better than people before him. He laid the ground for the modern understanding of the renormalization group. And Wilson noticed that the problem is really with scalars, because having a light scalar, in his way of thinking of the renormalization group, is like a statistical mechanics system, and we are near a phase transition, and a massless scalar is a point of second-order phase transition, and having a light scalar is like being tuned very close to a second-order phase transition. So imagine you have a chunk of material which has a second-order phase transition as we vary parameters like the temperature, the pressure, chemical potential, and so forth. And what we see with the Higgs is that as we sit in the lab, which is our universe, at the point where the Higgs is very light, the W and Z are very light, and that point is as if we turn the knob with all these parameters to be very near a second-order phase transition, but not quite at the phase transition. We are 1 part in 10 to the 34th away from that point. So again, this looks very strange. And this is the reason Wilson did not like scalars. I think he retracted that recently, but this is still right. And the scalar mass terms suffer from large quadratic divergences, and this is the root of the problem. So this is a more precise version of Weisskopf being a little bit unhappy about power divergences. So this is Wilson. But after that, now it comes to time that I remember, there was enormous confusion in the community what to do about these quadratic divergences, especially because we knew other regularization schemes in which there are no quadratic divergences. In particular, in dimensional regularization, there are no quadratic divergences. So some people said, well, this is an issue of doing Pauli-Villars or computing with some regularization scheme. If we just use dimensional regularization, the problem is not there. This is completely wrong. This thing I've just said is completely wrong. And I think this was explained by another luminary of 20th century physics. This is Steve Weinberg. And Steve Weinberg understood that the issue is not really with the quadratic divergences, but the issue is with the stability of the answers to changing the parameters at short distance. And the example he considered was the standard model. He embedded it in a bigger theory. In his case, it was some kind of grand unified theory. The details are not important. And he said, take this full theory with the 2 scales, and if you want, you can even use dimensional regularization for the full system. And now let's compute the parameters at low energies, the parameters of the standard model, as a function of the parameters of the high scale. And it doesn't matter which regularization scheme you use, the parameters at low energy are extremely sensitive to the parameters at high energy. Small changes of the parameters at high energy make huge contributions to the parameters at low energy. So the issue of the hierarchy is not quadratic divergences. Quadratic divergences is a way of probing it, but the issue is not divergences. In fact, renormalization group is not a statement about divergences. So we have this understanding of Weinberg, and the issue is stability of long-distance physics to small changes in short-distance physics. The last step in this story came from another giant of 20th century physics, Erhard H'Tooft, and he formulated a principle which really summarizes all this understanding. And he said that a dimensionless parameter in a theory is naturally small only if the theory becomes more symmetric when we set the parameter to be exactly 0. So his picture was that numbers cannot be small unless there is a good reason for that, and the reason should be a symmetry. And the stability we are after is set the parameter to 0. Now we have a symmetry. It's very natural that the parameter is 0. Now deform the theory a little bit, make small changes in the parameters, and as we make small changes in the parameters, the underlying symmetry controls the smallness of the parameter. So we'll refer to that as the technical naturalness, called after Professor H'Tooft. So I would like to summarize it in one slide. There are really two aspects of the problem. The first is the intuitive problem. The intuitive problem is, where did small numbers come from? Why doesn't dimensional analysis work? I mentioned that earlier. And a priori, we expect all dimensionless numbers to be numbers of order 1, so we'd like to understand how come they are smaller numbers. And the main thing I would like to emphasize here, that these are interesting questions, but often we can postpone the solution to higher energies. There is no guarantee that the explanation to this question, this is a good question, it needs an explanation, but there is no guarantee that the explanation occurs at nearby energies. The reason I emphasize that is that they should be contrasted with a more serious problem, which I'll refer to as the technical problem. And the technical problem is basically H'Tooft's version of the problem, is that if in some approximation we find a hierarchy, higher order corrections tend to destabilize it. So imagine that classically we managed to arrange a hierarchy. We set the parameters, we tune them very accurately such that we have a hierarchy of scales. Quantum fluctuations tend to destabilize the hierarchy. And intuitively it's clear why. We said that the hierarchy is sensitivity of the long distance properties, sensitivity to short distance properties. So small changes of the short distance properties make a big effect at long distance. Now in a quantum theory, everything fluctuates. So even if we tune something, it still tries to fluctuate a little bit. And these small fluctuations is what restores dimensional analysis. This is what ruins hierarchies. An example of that is level crossing never occurs in quantum mechanics because the levels repair. Things try to be numbers of order 1. So in quantum mechanics, dimensional analysis works better than in classical mechanics. And therefore, we have this issue of the technical hierarchy problem. And H'Tooft's way of organizing it in terms of a symmetry, we need a symmetry to control the hierarchy, is a good one. But if we don't have a symmetry, we are in problem. And so this problem, the technical one, is a more serious one than this one, and I'll soon give examples. And the main thing I would like to emphasize, again, this has nothing to do with quadratic divergences. The issue is really the underlying symmetry. And the main difference between the intuitive problem and the technical one is this line here. Here we can postpone the solution to high energy. There's really no need to address the problem right away. But here, we must solve the problem at the same scale. We have nowhere to hide. If we have a technical problem at some scale, the renormalization group tells us that we have to solve the problem at exactly the same scale. So let's go through the various hierarchies and examine them in view of what I've just said. So first I mentioned the fermion masses and mixing angles. They span 5 orders of magnitude. The masses span 5 orders of magnitude. And the mixing angles are small. Would like to understand why. And here, we have only the intuitive problem. Quark masses, lepton masses, and mixing angles are such that if we set them to be exactly 0, we have a new symmetry. So Professor Toft tells us, that's okay, we don't have the technical problem. We still need to understand where these numbers came from, where did this hierarchy came from. But since it's natural, technically natural, there's an underlying symmetry that controls it. We don't have to understand it right away, and therefore we can postpone the solution to high energies. So I see nothing wrong with the solution or the explanation of the spectrum of quark masses coming from Planck scale physics. There is no urgency in finding a solution right away. So in a way, this is the simplest of the hierarchy problems. As we go in the hierarchy of hierarchies, the next one is the strong CP problem. This is kind of an in-between situations. Here we have both the intuitive and the technical issue. The reason is that if we set theta QCD to be exactly 0, it seems that we gain a symmetry. Remember at Hooft's criterion, the criterion was we want to have another symmetry when we set the parameter to 0. So it seems that we get a new symmetry, the symmetry being CP in the strong interactions. And indeed, if we set theta to 0, the strong interactions preserve CP symmetry, but the full theory is not CP invariant. There is CP violation in the weak interactions. And the CP violation from the weak interactions tends to leak through quantum fluctuations into the strong sector. So there is no way to shield CP violation from coming from the weak sector to the strong sector. And therefore, we do not gain a symmetry as we set theta to 0. If we don't get a symmetry when we set theta to 0, we have the technical problem, and therefore, we have to solve it right away. Notice that in this case, we have only logarithmic divergences. Theta QCD does not suffer from quadratic divergences. This is a clear sign that the technical hierarchy problem has nothing to do with quadratic divergences. Here we have the technical problem with logarithmic divergences. Here there's another interesting fact that the coefficient of the logarithm turns out to be extremely small. And it's extremely small because of conspiracy of factors we understand. So that small number we understand. But it still multiplies this logarithm. And therefore, the strong CP problem is a problem that suffers from this technical hierarchy problem. And since it's the technical hierarchy problem, the explanation should happen now. There is no reason, there is no way to postpone the explanation. So in its simplest form, the explanations that people contemplated are axions. These are very light particles, or maybe m up equals 0. This is still controversial. And there might be something else. People also contemplated more elaborate solutions where the underlying physics is at higher energies, but I do not want to discuss them here. So these are two examples. And as we move up in difficulty, the next one is the Higgs mass and the electroweak scale. Here we have these quadratic divergences. As I emphasized, these are extreme sensitivity to high energy physics. We have to fine tune to the order of 1 part in 10 to the 34. This is a huge fine tuning. I would like to clarify that I said that the principle that we have to follow is there a symmetry when we set the parameter to 0? One might say that when we set the Higgs mass to 0 and we don't break electroweak symmetry, SU2 cross U1 is not broken, and therefore here is the symmetry. But the point is that SU2 cross U1 is always present, it's just not spontaneously broken. And when I say breaking a symmetry here, I mean explicit breaking. So in this case, we have both the intuitive and the technical problems. And hence, we expect to solve the problem now, at low energies, at TeV, in a way that the LHC can discover. And now comes, so I started with no technical problem at all. Then I talked about strong CP, which was in between. Then I talked about quadratic divergences and the Higgs. And now we come to the biggest hierarchy problem, the big elephant in the room. And this is the cosmological constant. Here the divergence is quartic. Here we need to tune 1 part in 10 to the 120. So this is unbelievably large number. If you wish, this is the biggest failure of dimensional analysis in physics. Do dimensional analysis, and we are wrong by 120 orders of magnitude. So this is clearly something we should understand. And 35 years ago, all of us thought that the cosmological constant, or maybe I should say most of us thought, that the cosmological constant was exactly 0. And there is some symmetry or principle or something that will explain why it's 0, and one day we'll understand it. And I remember very vividly that that was the consensus of the community, except that this was wrong, because now we know that the cosmological constant is not zero. And once we know it's non-zero, our ideas of naturalness are clearly beginning to shake, and maybe all these ideas of naturalness that guided us so well during the 20th century, maybe there's something wrong with them. So going back to the Higgs, what have people suggested? And they suggested two classes of solutions. I mentioned them earlier: strong dynamics or weak dynamics. Strong dynamics under the name of Technicolor and its various more modern reincarnations, and weak dynamics using supersymmetry. Unfortunately, Technicolor is basically dead. Different people declared it dead already in the 80s. With the mass of the top, it was really very uncomfortable. But as time passed by, it's really dead and rotting there. More recently, precision measurements of the S and T parameters, and finally the measured value of the mass of the Higgs basically put the last nail in the coffin. And the intuition behind that is quite clear. The precision measurements assume that the Higgs sector is weakly coupled. So we do some radiative corrections, and we compute the values of S and T, and the measured value is very similar to the computed value. The same is true for the mass of the Higgs. A light Higgs means that the Higgs self-coupling is small. Now we even know what the value is because we know the mass of the Higgs. So we know that the Higgs self-coupling is small. How can strong dynamics lead to such a weakly coupled scalar? Strong dynamics, as we know, say in QCD, gives strongly coupled scalars. So more intuitively, the measured mass of the Higgs tells us that it is weakly coupled, and strong coupling solutions like Technicolor tend to lead to strongly coupled Higgs. Now, there are more sophisticated composite Higgs models, and perhaps they could work, but they are very, very complicated and quite artificial, so let's not discuss them in detail. The second possibility is supersymmetry, and you will hear more about it later in this school, especially in the context of supersymmetry and naturalness. But it's hard to make supersymmetry fully natural. And the problem really comes from the fact that the Higgs, the problem with Technicolor was that the Higgs is too weakly coupled to come from strong dynamics. The problem with supersymmetry is the Higgs turns out to be too strongly coupled to come from supersymmetry. So in the MSSM, it's the minimal version of supersymmetry, the Higgs self-coupling is related to the gauge coupling. This is just one of the properties of supersymmetry. So it's not just a small parameter, it's a small parameter that we know its value. So we know the value of this small parameter, and indeed the tree level, the mass of the Higgs, is less than or equal the mass of the Z, and that's already wrong. The Higgs is heavier than the Z. Now, radiative corrections can allow the Higgs to be heavier, and most of the theoretical effort in making supersymmetry consistent and natural is how to push the mass of the Higgs from its natural value below the mass of the Z to larger values. And there are various ways of doing it. One possibility is to make the stop heavier. This is the supersymmetric partner of the top. The other is there are parameters called A terms. These are cubic scalar couplings in the Lagrangian. We have to make their coefficient large. Or we can go beyond the minimal supersymmetric model by adding more fields. So there are ways of doing it, pushing the Higgs from below the mass of the Z to 125, but that is challenging. So these three options are possible. These three options of raising the mass of the Higgs are possible. But if we want heavy stop, we need a lot of fine-tuning. So the same fine-tuning that we're set to solve comes back to bite us here, and it's known as the little hierarchy problem. Second thing is large A terms. They are logically possible, but it's very hard to write concrete models that produce large A terms and are consistent with the lack of flavor-changing neutral currents. And going beyond the minimal model is possible, but it has its own problems. So it's not to say that it's impossible to raise the mass of the Higgs to 125, but it starts feeling uncomfortable, and it's not easy, and we need a lot of gymnastics to do that. In any event, this is not kind of the first guess you will try when you write a supersymmetric model. And I don't want to use it's not the natural value for that. So what are the options about naturalness? Option number one, naturalness is correct. So maybe the LHC will find natural SUSY. and maybe there's some variant of the theory that is there. Maybe some other solution of the hierarchy problem could be discovered. The LHC will find some new particles pointing to new principles explaining the hierarchy problem, something that theorists haven't yet thought about. And the main point is that we'll know this very soon. So in a few years, the TV range will be explored, and we will know whether this option is viable or not. The second alternative is that physics at the TV range is unnatural. And that could come in various different ways. Way number one, a single Higgs and nothing else. We already know the Higgs is there. Maybe they will run the LHC and we'll just find the standard model and nothing else. This is still logical. It would be unpleasant, but true. We can also contemplate unnatural versions of supersymmetry, like split supersymmetry, and I'm sure we'll hear a lot more about it later in the school. There could also be some other particles. I mentioned some other possibility, maybe another scalar, another gauge field, another fermion. Maybe they are interesting, maybe they are not, but they do not address the hierarchy problem. So the main point now on the agenda is nature at the TV range natural or not? We are in this, the road splits, and we'll know in a few years whether we're going the natural way or the unnatural way, and this has important consequences. So if nature is indeed unnatural, and this is something that the LHC will tell us, we'll have to re-examine all our naturalness ideas. All this long historical description I gave you, starting with Dirac and ending with 't Hooft, this whole avenue will have to be re-examined. Was there anything wrong there? Or how should we think? Should we do physics in such an environment which is unnatural? So it's easy to summarize the situation in a flow chart. First of all, question, is there anything beyond the single Higgs? We'll know that very soon. There are two options, either yes or no. So if no, we should definitely abandon naturalness. If yes, we should ask, is electroweak breaking natural? So imagine we find some more particles. Do these particles point to a theory that gives us natural electroweak breaking? And again, there are two options, yes or no. No, again, we abandon naturalness. And yes, the world is natural, and we celebrate, and we continue. The next topic I would like to discuss is what happens if we are here. Imagine we have to abandon naturalness. How should we think of physics if we take this route? So the first route, there are tons of papers and a lot of people discuss that. Let's discuss the other one. So what if physics is unnatural? Imagine TV physics is unnatural. And unnatural, I mean, it's clearly nature, but it is unnatural. It's using the word natural. So the leading option is a landscape of vacua. The universe is huge. We live in a tiny part of the universe, and the theory that the parameters that we see are just characteristic of what's going on here. And if we try to ask the question, why is the electron mass what it is? Well, this is the electron mass here, and elsewhere the electron mass is different. And I asked before, why is the gauge group SU3 cross SU2 cross U1? And the answer is, well, that's the answer here. Elsewhere, the answer is different. And why do we have this spectrum of quarks and leptons? Well, that's the answer here, and the answer is different elsewhere. It's kind of getting boring after a while because every question can always say, well, that's the answer here, and the answer elsewhere is different. So the world is much bigger than what we think. The word that comes here is the multiverse. And the laws of physics are different in different places. The laws of physics are environmental. And predicting or explaining the parameters of the standard model, like the electron mass, might not even be the right question. Well, we have seen that before. We've seen that before in the study of the planets. So predicting the, predicting the mass of the electron in this framework is very much like predicting the radius of Venus around the sun. It has the value it has because that's the value it has. Or if you wish, it came from some complicated initial conditions, and it's not fundamental. And to make it more dramatic, I really like this historical example of Kepler. Kepler is known for his laws of motion of planets around the sun. But the law that Kepler was most proud of was a beautiful law, which turns out to be completely wrong. He knew of 5 planets at the time, and he wanted to correlate the sizes of the orbits of the 5 planets with the 5 platonic solids. This really sounds great, we have deep mathematics that there are 5 and only 5 Platonic solids, and their sizes are related by pure numbers, 4 to 1, that relate their sizes. And what would be more natural and more beautiful and more connected to deep mathematics if the orbits of the planets were coming by the same principle? This is it. Well, this is totally wrong, and it's wrong for many different reasons. All of them are interesting. First, experimentally, it was wrong. Even Kepler realized that the numbers didn't match his beautiful theory. That's good. Second, we have more than 5 planets. There are only 5 Platonic solids. So even if the measurement was not accurate enough, the theory doesn't hold water. But what's more important is we understand now that this is not the right question to ask. It's not just the wrong answer. It's also the wrong answer, but it's the wrong answer to the wrong question. The deep thing that Kepler did was his other laws, which eventually gave birth to Newton's theory of gravity, the 1/r² force between the planets and the sun. So the relations he found between this time going around the sun and the size of the orbit, all these things eventually were derived from a deeper principle. So what we see here is that some of the parameters, like ratios between, some relations between the parameters are deep, related to deep truth, and some values, like the size of the orbit, is not deep. So the question we have to ask ourselves with the analogy today, if we are in this situation where the parameters are environmental, how should we even think about it? Which of the parameters in the standard model are environmental, and which of them really reflect deeper truth? So this turns out to be the wrong question. And this is what I've just started saying, is that in this case, if physics is indeed unnatural, should we attempt to solve the other naturalness problems? Which of them should we solve, and which of them shouldn't we? Which of them should we blame on the environment, and which of them really reflect deep underlying physics? More generally, what are the right questions to ask and to explore? Can we just give up on parameters we cannot predict because they are environmental, or should we study the distribution of such parameters in all the vacua, in the whole universe, and hope that we are in a typical situation? Or maybe that's the wrong way of thinking about it. Well, some might say that we should stop looking for deeper truth at shorter distances. Instead, all the parameters are environmental and should not be explained. This would be extremely disappointing. Over the last few centuries, the guiding principle of physics, or science in general, was reductionism. We always tried to look for deeper and deeper reasons at shorter and shorter distances, which gave us understanding of what happens at longer distances. Classical mechanics was derived from quantum mechanics. Chemistry was derived from the rules of quantum mechanics, where we study atoms and the electrons and the motion there. Nuclear physics was derived from the existence of nuclei and the forces between them, and eventually all that was replaced by a deeper truth, which is the standard model. So we have had quite a successful run for several centuries of this onion of layers and layers of complexity, going deeper and deeper to shorter distances and finding deeper principles. Is this the end? Is this where we give up and say that from this point on, all the parameters are environmental, there is nothing to explain? I find that very disturbing. Is this the end of reductionism? But if so, we have kind of a very strange coincidence, which really bothers me. 3 things happening at the same time. First, it seems like if this is the case, we are approaching the boundary of theoretical understanding. We have had such a run for several centuries, and that's it. Here we are in the beginning of the 21st century with the end of reductionism. All the parameters are environmental. There is nothing to address, nothing to understand. Very depressing. The second thing that coincidentally happens at more or less the same time is a technological barrier. Yes, the LHC will run at higher energy. This will be in a few years. And maybe we'll get another factor of 2 in energy, and people even contemplate having another factor of 7, and maybe even a factor of 10, and then ingenious physicists will give us 2 orders of magnitude. But it's really hard to imagine mankind going to energies which are much, much higher than that. Hopefully I'm wrong about that. But this is really coincidence, that the theoretical barrier at 1 TeV happens at exactly the same point where the technological barrier of our ability to build accelerators and probe shorter distance physics, and finally now. So this sounds like a lot of these problems of coincidence in cosmology, which also ask for an explanation, and makes me believe that this line of reasoning is wrong. And it's not true that we face the end of reductionism. But either way, we're at a junction in the road. Either we take the natural route or the unnatural route, and the LHC will give us the answer. So this is really exciting. So in conclusion, what can the LHC find? Option number one, no discrepancy with the minimal standard model with a single Higgs. This is definitely correct as of today. There are all sorts of rumors that come and go, but some of them come, others go away, and then others come, and so forth. As of today, there is nothing definitive here. No discrepancy with the minimal standard model, but we have a few more years. This will be very exciting. Next, there could be new physics beyond the minimal standard model, but it does not address the stability of the weak scale. I gave an example, say, of another gauge field, another fermion, which just happens to be there. So this can happen. More exciting would be a natural explanation of the weak scale. I mentioned three options: supersymmetry, that's weak dynamics; strong dynamics, like Technicolor, warped extra dimensions; or something else we have not yet thought about. And I really want to emphasize that this menu of possibilities will disappear in a few years. So if there is a talk here in a PITP, say 10 or 15 years from today, these options will not be on the slide. We'll know the answer. So this is not something for the far, far future. This is something we'll know very, very soon. Now, all these options are interesting. It's not that one of them I might personally like more and you might prefer another one, but all of them are interesting. First of all, they're correct. We'll know what the answer is. We'll not need to speculate. We'll know what the answer is. We'll look at the numbers. We'll have reliable information about nature. And they point to a very deep property, this naturalness idea, which also has interesting philosophical implications. Is our world natural? Is it special? Are we at a special universe? Or are we at some random point in some very, very complicated, huge multiverse? Is this the end of reductionism? So it's interesting that some very sophisticated technological device sitting in Geneva can give us deep philosophical conclusions. And we'll know very soon. So we are in a win-win situation. Every outcome is interesting. I would really like to know which road, which side of the road do we take? Are we going the natural way or the unnatural way? So the future will be exciting. Thank you. If there are any questions, I'll be happy to answer. And if you're embarrassed to ask in public, I'm around for the next 2 weeks. Feel free to come and.
You said that in the limit Higgs goes to 0, there's no symmetry restored to the standard model. But what about scale invariant?
The standard model is not scale invariant. And this is one parameter that is scale invariant, but there's also lambda QCD, which also breaks the scale. And in general, in quantum field theory, it's very hard to get scale invariance. And nature around us is not scale invariant. So radiative correction, even if the Lagrangian respects scale symmetry, like, say, the Lagrangian of Yang-Mills theory, the full theory is not scale invariant.
Yes, so you mean not just from the classical level?
That's right. I'm talking about the full quantum theory. And that's where lambda QCD came from. The scale of QCD is. So when I gave before the explanation of Dirac's question about why the mass of the proton is so much lighter than the Planck scale, this is really because of this story of asymptotic freedom, the breaking of scale invariance, and so forth.
So when you say that supersymmetry solves the naturalness problem, it is commonly said that the supersymmetry eliminates the quadratic divergences by the cancellation of the bosonic and fermion loops. But it guarantees the stabilization of the some scale with respect to the quantum correction. But how supersymmetry explains the exponentially small scale generation itself?
Okay, I'd like to say two things. First of all, I would like to correct a commonly stated mistake. The commonly stated mistake is that in supersymmetry there are no quadratic divergences. That's not true. There are supersymmetric theories with quadratic divergences. Let's just get this mistake out of the way. It is true that in the minimal supersymmetric standard model, there are no quadratic divergences. This is true. And that's one aspect of stabilizing the hierarchy, but we would still have to face the intuitive aspect of the problem of why is it that we get this discrepancy of scales. And the idea, which I think goes back to Witten, is to break supersymmetry dynamically, to produce the discrepancy of scales by this formula that I had, this exponential of 1 over g squared, e to the minus 1 over g squared. So g is small, but not very small, but this e to the minus whatever is an extremely small number. And there are ways of building models that do that. They are quite complicated, but it's not impossible. But maybe nature didn't pick this option. Like, it's not up to us to decide what option nature picks.
And is the supersymmetry essential to such a dynamical generation of such scale?
So in these models with dynamical supersymmetry breaking, the extra scale is generated dynamically. The same way as I answered the question before, the same way lambda QCD, the scale of QCD is generated dynamically. So in these models, we start with a theory that classically there's scale invariance, but quantum mechanically a scale is generated. It's naturally much smaller than the cutoff scale or the Planck scale, and that triggers all the other breaking.
So why does dimensional analysis also include the fact that you want order 1 numbers? Like why is the importance of, normally when you learn about dimensional analysis, you just say you use the balance of dimensions. But now it seems like part of the principle is you use the balance of dimensions and there's always an order 1 coefficient.
Well, the dimensional analysis never tells you the dimensionless coefficient out front.
But so,
And now there's no fundamental law of nature that tells you that these dimensionless numbers are order 1, but this has been our experience, like the volume of a sphere, the area of a sphere. All the problems in geometry, there are some powers of the radius coming from dimensional analysis, and then there's some number that has to be computed. It might be pretty big. It might be 4 pi square, which is 40. And there are other situations like that. It might be that this is something we have to put on the computer, like computing the spectrum of glue balls in Yang-Mills theory. There's one scale in the problem, and the whole spectrum of glue balls are numbers of order 1 multiplying that scale. And the computer should spit numbers at the end, and these numbers will be numbers of order 1. It might be 10. We have examples where the numbers of order 1 coming from, say, strong dynamics are 1 over 20, and then we are baffled. Oh, why is it so small? Why is it 1 over 20? We have no example where it's 10 to the 34th. We have no example where it's 120. And it's kind of natural. This is the way physics works. And it's not coincidence that it's called natural.
So when you talk about technicolor, you said strong coupling tends to produce particles that interact strongly with one another. If I think to pions in QCD, so they are strongly coupled objects by their nature, and their lightness is due to chiral symmetry. If I think to the decay of a pion to a muon and a neutrino, it's a purely electrolytic process. So in this case, it's a strongly coupled object, but they can have weakly coupled interaction.
That's right. That's why I talked about the self-coupling. So the analogy there is to think about a sigma particle. So there is a description of chiral symmetry breaking using 1 sigma and 3 pions. The sigma barely exists in nature. It's kind of a very broad resonance that we can argue whether it's there or not. But to the extent that it is there, it's very broad. Why is it very broad? Because it's strongly coupled. The coupling of pions to sigma and the sigma to itself are very, very large numbers, and that's why the sigma is so broad. And that's not surprising. The sigma came from strong dynamics. Whenever there's strong dynamics, the couplings will be numbers of order 1. You're not going to get tiny couplings.
So you have in mind a real technicolor in which the Higgs is the sigma.
That's right. So with exactly. So this is in the simplest version. There are more sophisticated version and with exponentially increasing degree of sophistication, and maybe they work a little better. They are not perfect. As far as I know, there is no model that is consistent with everything we know, that gives quark masses and so forth. See, one aspect of the problem is that I did not emphasize it. It's very hard in Technicolor to give masses to the quarks. This is what I alluded to that by saying that it was basically dead in the 80s and the 90s, and that was the challenge. And again, people wanted, the naive Technicolor does not give masses to quarks. So there are various extensions of it called extended Technicolor and various variants of it, which were designed to give masses to the quarks. They don't work very well because you had a very elaborate mechanism that you needed to do. You needed a very elaborate mechanism to explain the quark masses. It became really almost impossible with the top quark, given that it was so heavy. And the biggest challenge there was to make everything work together with flavor-changing neutral currents, which are very strong bounds from nature. And I'm sure you'll hear more about all these ideas later in the school.
But after with the partial compositeness, now maybe it's more difficult to give mass to the leptons, which are light, than to the heavy quarks.
Yeah, so when we talk about, we started making the model more complicated, partial compositeness or other ideas of composite Higgs. Yes, it's logically possible, and maybe we should just add a few more handles and a few more sectors and couple them, and maybe it works, but at some point it looks artificial. That's why I use the word artificial. At some point you could just say, well, maybe just one Higgs and that's it. This is clearly the simplest solution. It's not technically natural, but if the model is very complicated, then yeah, but if you could, this is correct, but if you add singlets, if you really want the example, first of all, you can go to higher dimensions and then there are power divergences in supersymmetry. Yeah. So first of all, if you want so you basically want you're asking about my comment to the question from here about higher dimensions. So first of all, in higher dimensions, we have supersymmetry with power divergences. That has nothing to do with so we can easily get power divergences in supersymmetric theories. Even in 4 dimensions, even in variants of the standard model, the MSSM, if we add singlets, we can get power divergences in soft terms. If supersymmetry is broken, there are soft supersymmetry breaking terms, and they lead to power divergences. It is a fact that in the MSSM, there are no power divergences. That's a correct statement. No more questions? Thank you for listening.